So if we do regular quantum mechanics, then any problem can be formulated as diagonalizing matrix, solving time-independent Schrödinger equation with big or small basis. And if the equation becomes really highly dimensional, very many degrees of freedom, including, for example, multi-electron effects, multiple degrees of freedom, this diagonalization of huge size matrix becomes a little more expensive than we may wish. From practical point of view, perturbation theory, more specifically time-independent perturbation theory, is a way to avoid this diagonalization. If we consider Hamiltonian summation of two parts, one unperturbed leading part and very small perturbation, then the correction to energies and wave functions can be added analytically without solving for the whole Schrödinger equation. That's basically it. So let's practice it on the simplest possible example, which will be really silly. It has almost no practical reasons because the theory is needed for huge matrices. But we will consider 2 by 2, which can be solved by pen and paper or by human's hand really quick. But we will use it just as a test for the theory. So there is many sources for the perturbation theory. We will derive it tomorrow in the class and continue on, but you can just go online and look into Wikipedia. How do equations look like? So if we, I have already closed this page, but what should we do? I have an idea. I will just scratch a couple of equations in the blackboard. Where is the board? This is much more interesting than the content of our meetings itself. So when we have our Hamiltonian as summation of zeroth order unperturbed and perturbed Hamiltonian, then the wave function is a summation of zeroth order plus first order correction plus second order correction and so forth. And the energy is summation of the energy of zeroth order plus first order correction plus second order correction and so forth. Right? We do have this idea. Then there are conditions. This all will work assuming that H1 is smaller than H0. So it is something that corrects the Hamiltonian a little bit. Some small external perturbation, which will be like unharmonicity or what we considered on your presentations, ligand field to the metal organic complexes. And Levi did present spectrochemical series where ligands can be ordered according to how strongly they affect the energy splitting of the d orbitals. And some ligands are really big, so they perturb very small splitting. So you can consider absolute value of the energy and amount of the electrostatic field that these ligands impose on the central ion, on the orbitals, as a small parameter. And if this parameter is small, then this could be considered as the perturbation theory. So first we solve for unperturbed Hamiltonian when there are no ligands, and then we slowly bring all, if it is octahedral, all 6 ligands from infinity closer and closer to the metal ion, and see how do they start to affect the splitting of atoms. Small. So E0 just comes from solution of Schrödinger equation without perturbation, and then the correction of the first order is the matrix element based on the interaction between orbitals, unperturbed orbitals, connected through the matrix element of this interaction, each one. So if there is a perturbation, then it allows, there is a non-zero matrix element, means there is a specific energy of interaction between these basis states. And if you take them into account, it will give the contribution to the energy. So because of the additional interaction, energy levels will split. The second order will be same term, but in the matrix element of interaction calculated in the basis of zeroth order wave functions divided by zeroth order energies difference in the denominator. And then this one, and this one are plugged in. And then we are getting this result that comes from the summation of the series will be is assumed to be very close to the solution of energies that appear from solving the exact Hamiltonian. So the benefit if everything is correct, then the benefit is that we solve Schrödinger equation, which is diagonalizing matrices of very big degrees of freedom, big dimension, only at zeroth order, and sometimes we know the solution. And then for the corrections to the energy, we just do summations and fractions and finding matrix elements, which is substantially cheaper. That's the basic idea. Questions, objections? No questions? Yes?
square after the bar square?
Yes, yes, it should be square. Absolutely correct. Yes. Thank you, dear. Wikipedia.
Can you just do the bottom half, like the bottom triangle and times by 2? Or is it not always symmetric about the diagonal?
Bottom triangle.
So you have your matrix, you have your diagonal, the bottom triangle, top triangle. Are they not symmetric?
It's a Hermitian. It's the matrix Hermitian.
Well,
right?
Yeah, for like the sum. Because if you do,
Well, not for the sum makes the matrix a number.
yes, but doing your conjugative product, you just do
no, over the whole matrix. And there are corrections to these corrections. There are additional equations specific for non-degenerate and degenerate cases that we will cover later. Yes?
What is the square? Isn't it you're getting diagonal?
Huh?
Why isn't it square? Do we need a square?
We do need a square.
I mean, but I don't really
Why? Well, our meetings in class, which will be tomorrow, and then we will be not limited by necessity to do something practical. We will just discuss and draw equations on the blackboard, the whiteboard. Non-practical stuff, yeah. Sense. But then we'll consider the proof why the square is not.
But this one is supposed to give us the energy, right?
Yes, matrix element.
Matrix.
So the dimension of the nominator is energy squared, denominator energy. If you divide one by another, then the dimension is energy in the first power. Okay?
That E, that's not E squared on the left hand side. That's second order correct. That E in the bracket, in the parentheses.
Here
on
is
the left hand side, on the E, on the left hand side. That's not E squared.
this one.
Yeah,
It's
that's not E
order
squared.
of correction. It's you can do like prime, 2 primes, or do Roman numerals if you like to. Good.
Yeah.
Okay. So let's. No. Ding, 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 ding. Smile, you are on tape recording.
next week I'll have to sit over there.
Well, I will. From month to month, I will learn how to operate it more versatile, in a versatile way. Maybe put it on a tripod. And if you bring just such sort of camera to MMS, then we do not need to go here. Okay. So you do have a script that has been like pre-made, and let's go through it and make sure that we agree with it. But what do we do? What the script is for? So it implements perturbation theory, time independent, up to second order for two-level system. So if we do not need perturbation theory, actually we do not need computer for these problems. It is only for visualization. So we can take the unperturbed Hamiltonian containing only diagonal elements, energy plus and minus on the diagonal, and then we do add the perturbation, which will contain off-diagonal elements. So mechanically, it means it will mix. It adds interaction between these two levels, and then we will add together zeroth order and first order Hamiltonians in matrix form, right? And then on one hand, we will diagonalize it. On another hand, we will find corrections by perturbation theory. And then we will check how the exact solution and perturbation theory solution look compared to each other. Most of the time will be spent, or is already spent, just looking on the code. Very short time, but with practical necessity, is to look on the output of the code, which will be energies of the states as function of the perturbation of this V, value of the V, and checking which of the orders of perturbation is closer to exact solution. Your personal practice, maybe you can formulate it as a little homework, is to compare a couple of regimes when perturbation is much bigger than unperturbed energy and when it is otherwise, and see which order of the theory, of the perturbation theory, works better. So if we do only this diagonalization, then we'll get only one set of data points: energy of first level, energy of second level, as they are split. But it is very boring, and it is not for humans. It's numbers. But if you will scan the value of the perturbation, then we can look on the trends. So let's place this stuff into the cycle, and the value of perturbation will linearly grow. It will scan through different values. Make sense? Okay, and then upon the diagonalization, let me bring up this couple of lines. So if we diagonalize, then we get two sorts of answers: eigenvalues and eigenvectors. Eigenvalues will be on diagonal, and eigenvectors will be amplitude of probabilities that new state is distributed over basis states of unperturbed, which we will skip for now, otherwise it will be too long. And the energies are stored in the matrix, but we do not need the matrix. We need to just two values. So this command dd equals diagonal of d, it will just parse the diagonal values of the matrix. And then we do, well, the screen is not the best name for the variable, but it is for screening different values of the perturbation. So we accumulate, at each step of the cycle, we accumulate the values of the eigenenergies into this array. And then, let's keep the perturbation for now. And then after we are done, we are plotting this first and second component of the screen with continuous line. So here we select the such values that energies of orbitals are plus and minus 1, which later you can change, and then the exact solution is shown with continuous line, solid, in something that you can trust. Is it visible enough, or you want thicker lines?
Are these all dotted lines? These are all dotted.
Dotted lines will be, and dashed lines will be explained later. Let's look only on the continuous line.
Okay.
Okay? So as we increase the interaction, the energies which were plus and minus 1 before, they start splitting.
Is there a continuous line?
Here, let me highlight it. But you can just download the code that I send you as an email and run it with MATLAB that is installed on all these computers. Sorry if I didn't announce it before. I thought please have this code on your screens.
So if we run it,
Yes.
get those
If you run it, the graphical screen will pop up at your, a panel will pop up at your screen, and you'll see these images. Please raise your hands if you do not see it. Okay, now positive test. Please raise your hands if you see a picture like this on your screen. Perfect.
I almost want to lazy route to shut my screen.
Okay, so this solid lines is our reference point, which is obtained by solving exact Schrödinger equation with perturbation. Now our goal is to obtain similar trends by different alternative bypass by different theory that avoids diagonalization. So what we are trying to do is to so here we set up the zeroth order correction, which is just unperturbed diagonal elements of the Hamiltonian, and we place them into screen 0, and then we plot them. So screen 0 is dotted line. So it is the same as for zero perturbation all the time. Even if you increase perturbation, zeroth order doesn't change, right? Logical. Now for the first order perturbation, we take V and minus V. So it is just adds linearly to the energy, and this is shown as the straight line here. And if you go to the second order, it is same stuff as shown here on the board. So interaction of diagonal element of the perturbation Hamiltonian to the second power, so h12 squared or h21 squared, which will be the same because we have v here and there, divided by energy offset of the unperturbed energy. So Hamiltonian, unperturbed Hamiltonian first diagonal element minus second, and or second minus first. So this one And now we just go to the plotting. The second order perturbation is plotted as screen 22, and it is plotted with dot dashed lines. Let me highlight it so that we see it better. So this highlighted stuff shows the results for energies of this seaweed model, but they are obtained without diagonalization. It is the silliest thing in the world if we apply it to 2 by 2 matrix, but as soon as we get like 100 million by 100 million matrix, it could be a little helpful. So it is, if you have doubts in necessity of perturbation theory, ask in private opinion of Diane. I think he will be one of the biggest supporter of this theory, right?
Well, I'm a supporter.
You are good. Good. Well, nothing in field, all field theory cannot be done without perturbation. It's like based on it. You cannot diagonalize this multi-electron, multi-particle interaction. No. So perturbation theory is only way in the field theory. Okay. So what you may want to do is to modify two parameters in the first two lines, total energy and not total, parameter E and parameter dV. So relative order of the perturbation and the unperturbed energy, and see the trends. So what we can see right now is that in the figure for the parameters that are brought up at the screen, that for the value of perturbation up to 1, so until the value of perturbation becomes comparable to energies of unperturbed states, the second order perturbation theory provides relatively good coincidence with exact solution. See, this solid line and dot dashed lines coincide, or at least go close to each other until the value of perturbation reaches 1. If we increase it further, it starts diverging. Okay, I'm done. I don't know how to formulate a homework. Maybe we'll formulate it in class, but you may practice it and save the image. Like, do a couple of values for E and dV, generate the figure, and send it as an image to yourself, so that later you will decide how to analyze it.
Looks like you might be negative. Doesn't matter. See, it's
I
like by
saved
saying
two.
original first order
It
starts
two.
being useful as high rows.
I saved two. So I saved an original copy and one that I would change. No. Yeah.
You know how to save images and send them to the source?
I just
Catch
copy
this.
the code and on my machine. My
Okay.
machine will produce it.
Okay. So you have MATLAB installed on your.
Oh, I have Octave.
No, do this. Octave will do calculation that may fail in images.
No, it does.
Okay. Just in case. I'm not insisting.
Okay. I have to install. How do I install MATLAB on my machine?
You can get it via a USU. You have to email. Yeah, you have to email someone in IT, and then she'll give you a form, and then you fill it out, and then you give it back. Then she won't give it to you.
So, any questions you anticipate to ask in the nearest few minutes? Seems straightforward.
What are we supposed to be doing?
I'll just run it a couple of times, save the image, and then we'll decide to do what to do with it later.
I kind of got sidetracked on making a key because I like to a key, a ledger,
Uh-huh.
because I like to know what each line means instead of just having a line pop up.
Oh, okay. Solid. Exact solution of Hamiltonian.
Yeah,
Dotted, unperturbed, zeroth order. Dashes, first order. Dot dashes, second order. More questions? If no, I am putting us out of record.